Maybe. Sweet. All right. My plan, my hope, my goal is to finish 3.1. Ooh, it's not what I want. My plan is to finish 3.1 today. Okay. We still got a decent chunk in that topic, but I think we can do it. If we have a little bit of time at the end of the class, we'll give you some time on topic 1 for unit 3. We haven't turned a homework assignment in a really long time, which I'm sure you're upset about. So I'd like to remedy that and give you some homework. Unit 3, topic 1, let's try that, will be due next week, Tuesday. Plenty of time. That's like almost a week still. But it's basically on all of this stuff. Okay? So just to keep that in mind, if we have a little bit of time at the end of the hour, we'll let you get started on it. It's pretty much 3.1 and nothing else. Because 3.1 is kind of a big deal if you haven't caught on, because we've been talking about it for a good 4 days already. Okay? So let's start here. This is where we left off in your note packet. I hope you can find this. I think it's somewhere on the 3rd page, give or take. But either way, find this in your notes. This is more of a recap. I put it in the middle. I don't know why I put it in the middle, but that's where it is. And this is saying that London dispersion forces are blank, 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 blank. Okay? These are sometimes called, not very often, but every now and then, these are called instantaneous. Ooh, wow. Instantaneous dipole induced dipole attractive forces. Okay? Now, I will almost never call them that, but this name is actually more descriptive than London dispersion. London dispersion, the term London is a last name of a dead white guy. Okay, great. Dispersion, that serves a purpose. Okay? These intermolecular forces, if you remember, these are the ones that happen because the electrons are in constant motion, right? The electrons are moving, and when they're moving around, we get these little tiny partial charges because they sometimes are unequally distributed, okay? They are dispersed in a weird way. That's where that kind of comes from. But calling them London dispersion really doesn't tell us much. This is actually more descriptive. Instantaneous dipole. That means at some random instant, you get a partial positive and a partial negative, right? The word dipole means partial positive chunk or partial positive region, partial negative region. So at some instant, you get a dipole, and then that dipole will induce another dipole on its neighbor. That's what London dispersion forces are. Again, these are the weakest type. It happens because electrons are moving around. And sometimes they're called this. More often than not, we will just call them London dispersion forces. You can abbreviate this LDF if you would like. We'll use that later when we start trying to identify them in the last little table that I've got for us. But anyway, that's just a little recap. Let's try a problem. Bromine boils at 138 degrees Fahrenheit. Now, Fahrenheit is the dumbest temperature scale of them all. I don't know why I chose it in this instant, but we'll never really use it. It's still technically it's okay, it works. We use it for weather in the United States, but really, it's a pretty dumb temperature scale compared to the others. The others are much more meaningful and useful in how they're structured. And I'm talking about degrees Celsius and I'm talking about Kelvin. Okay, those are much more logical, but you know, America, so we're going to use the Fahrenheit stuff. Anyway, but let's look at this comparison. We have bromine and iodine. Now, bromine and iodine are both diatomic. They don't exist as Br and I, but instead they exist as Br2 and I2. They are diatomic. This is like completely worn down. This used to be like a little nub, so it wouldn't scratch and screech. I don't know if I can prevent much of it. What color you guys want? All right. Can I do like more of a salmon-y? I don't want it to be too light. That's my only concern. All right, so these are both halogens. Why is there a difference in the boiling point of bromine versus the boiling point in iodine? Okay, that's the question I'm asking here. They're from the same family. They're from the same column. Their boiling points are pretty different. Let's look at this. Let's think about this. All right. We could do a Lewis diagram for each if we want. They're both pretty darn simple. It's just diatomic. So the bromine, you'd have Br, you'd have one bond, you'd have Br. And if we wanted to do all the Lewis or the lone pairs, we totally could. That's how diatomic bromine would be structured. Diatomic iodine is literally the exact same. That's a dot, I swear. Okay. Polar or nonpolar? Are these polar or nonpolar molecules? Nonpolar. That's a bromine. That's a bromine. They have the exact same electronegativity, right? Those electrons in that bond are shared perfectly equally. That means it's nonpolar. So this is nonpolar. This is also nonpolar. I'm going to steal a different marker on a different day. What types of intermolecular forces would each of these have? You got three choices that we really look at, right? You have hydrogen bonding. Do you see any hydrogen? Spoiler alert, if there's not a hydrogen, it's not going to happen. Okay? You have dipole-dipole intermolecular forces. Those happen when you have partial charges, when you have polar molecules. Are these polar? Nope. The last type of intermolecular force we talk about is London dispersion. Everything, absolutely everything has London dispersion. That's what we have here. This bromine has nothing but London dispersion. The iodine has nothing but London dispersion. So what's going on? Why is there a big difference, or why is there a difference at all in the boiling point of bromine versus the boiling point of iodine? Anyone want to take a crack at that? Not saying you have to give me the most profound answer in the world of chemistry, but just a general kind of shot. What could we deduce as the reason why iodine is a higher boiling point? Yeah, Jake.
Just because they're different substances.
They're different substances, but let's get down to what the difference is. What's the difference? Yeah. Good guess. But the electronegativity stuff is only going to give us like potential partial charges, right? But they're both the same. They're both the same. So the whole electronegativity thing doesn't come into play in this example. It's usually a good guess, though. Electronegativity applies to a lot of stuff. Also a good guess, but not quite. I thought you were going to say it, Luca. Yeah.
Because iodine has more.
Yes, let's go there. Now we're getting closer. I'm going to tweak it just a smidge. Iodine is bigger. It has more electrons. It is more polarizable, is the word. This is a bigger molecule. With more electrons. And I'm going to do electrons as E minus. Okay? It's a bigger molecule with more electrons. What that means is that it's more polarizable. Therefore, iodine is more polarizable. Now, polarizability is all about how much I can manipulate the electrons. If you can push and move them and manipulate them more, you get bigger partial charges. This is London dispersion forces and nothing else. This is London dispersion forces and nothing else. But iodine is bigger, it has more electrons, And as a result, when the London dispersion forces occur in iodine, they give you bigger partial charges because there's more room to move those electrons around. And there's just more electrons in general, which as they are moving around, you get slightly larger partial charges. And those slightly bigger partial charges give you a stronger London dispersion force, a stronger intermolecular force. And it's April, right?
Yeah.
Okay, so going back to what you said more molar mass. That works. That's a good way to remember it, right? It's not because of the molar mass that this has stronger intermolecular forces, but you can totally use that as like an indicator. Generally speaking, things with more mass have more electrons, and they're generally bigger. It's really the electrons and the size that give you that it's more polarizable, but saying that it has a bigger molar mass kind of leads to those two things. Make sense? Cool. Questions? Let's make another comparison. This time's a little funkier. Okay. A sample of 2,2,3,3 tetramethylbutane. Don't worry about that too much. But a sample of 2,2,3,3 tetramethylbutane has a lower boiling point than a sample of octane. Now, I have two pictures. This guy is the octane. That guy is the 2,2,3,3 tetramethylbutane. Blah, blah, blah. Okay. Just to clarify, because we're going to be referencing which one's which and all that good stuff. These hydrocarbons, by the way, you see this term? Hydro means hydrogen. Carbon, of course, means carbon. Molecules that have hydrogen and carbon and a whole bunch of nothing else are called hydrocarbons. Just to point that out. These hydrocarbons have a different structure, but the exact same formula. They are blank of one another. This is a new term. This is called isomers. Isomers of one another. An isomer is a different arrangement of the exact same atoms. Both of these molecules are C8, H, what do we got? 18. Okay, that is the formula for both of these. The exact same formula, just a different way of kind of organizing it. That's called an isomer. Okay, since the molar mass is the exact same, our first guess is that they would have the exact same amount of London dispersion force. Neither molecule has a dipole. This is really important, this last little chunk. Maybe not. I'll take that back. I was thinking it was going to say something else. Neither molecule has a dipole, and hydrogens and carbons never show hydrogen bonding attractive forces. So these are nonpolar. They have London dispersion forces, nothing else. They have the exact same number of electrons and the exact same mass. So we can't distinguish it the same way we could in the last example. In the last example, it's like, hey, here's some bromine, here's some iodine. Both nonpolar. They only have London dispersion forces, but this one's bigger. It's got more stuff. It has more electrons. It's more polarizable, higher boiling point. In this one, it's same exact formula, same exact mass, same exact electrons, but they do have different boiling points. Okay? They have different boiling points. Do I have that on your sheet? Do I have boiling points on your sheet? Hope I do. Huh. What am I doing? All right, well, let me talk about it. We don't have the actual boiling points on the sheet. I can look them up and show them to you later if you don't believe me. But these two molecules have different boiling points, despite being the same formula, the same mass. And it has to do with surface area. Okay? This one is very long and very flat. This one is kind of more compact, and you can think of it like a ball. The flatter, longer molecules have higher boiling points than the more compact ball-shaped molecules. Okay? So this would have a higher boiling point. This would have a lower boiling point. I don't know why I made the capital, whatever. Okay. Surface area also matters. The flat ones can kind of stack right on top of each other, all kind of nice like, and there's a whole bunch of little spots where these London dispersion forces can happen. The more compact one, the more spherical ball-shaped one, they don't pack as nicely. They pack more irregularly, and there's less spots where London dispersion forces can happen. Okay? So we'll conclude this on the next slide. Since the boiling points are different, we know that the substance with a higher boiling point must have more, ooh, that shifted, intermolecular force of attraction. Okay? Again, when you try to boil something or undergo a phase change of a substance, you're breaking intermolecular forces. Higher boiling point equals higher intermolecular force, stronger intermolecular force. Octane is much longer than 2,2,3,3 tetramethylbutane and exposes a greater surface area to neighboring molecules. The greater the surface area, the greater the London dispersion forces. 2,2,3,3 tetramethylbutane is more compact than octane, so there is less surface area to neighboring molecules and less London dispersion forces, and therefore it has a lower boiling point. Okay? This is a unique comparison. AP uses this every now and then on the test. Because generally speaking, the easiest comparison is, hey, look, these two things have the same type of intermolecular force. That one is bigger, that one has more mass, that one has more electrons, that's got stronger forces. This example is same exact formula, same exact type of forces, same exact mass, same exact electrons. The only difference is how it's shaped. Long, flat molecules have stronger intermolecular forces. They can stack nicely together, and that gives you stronger London dispersion force. Kind of an obscure example of what we're going with. Yes, Nick?
So is there like a physical difference between those two?
Like how they would exist in the real world?
Yeah.
Yes. Now, if I'm not mistaken, I think they're both liquid at room temperature. I'd have to look it up. But I'm pretty sure their boiling points are maybe like 30 degrees apart. They would have similar properties kind of across the board, but yes, there would be subtle differences between them. Yep. Good question though, right? Because it's like the same formula makes you almost think it would be the same stuff, but it'd be very close. They're very similar, but not perfectly the exact same. Use fluorine and whatever else you need in a sketch that clearly shows hydrogen bonding attractive forces. There's fluorine. I'm going to bond it to hydrogen. That's one hydrogen fluoride molecule. If I want to show a hydrogen bond, I should probably have a second molecule, don't you think? Because it's an intermolecular force. You can't show an intermolecular force unless you got two molecules, minimum. So over here, I'm going to draw another. Which is more electronegative? We'll go pink and purple today. That's just for fun. Fluorine is way more electronegative, right? That's the most electronegative. So what partial charge do we get over here? Partial negative. The electronegativity means it's drawing or pulling the electrons towards its nuclei. And on the opposite side then, as these electrons are pulled away, we get a partial positive to that hydrogen, right? Same thing is true on the next molecule. I apologize for the squeaks. I can only do so much. That's partially positive, that's partially negative. and there's an attractive force that forms between them. That's a hydrogen bond. Hydrogen bonding only occurs if your hydrogen in the molecule is covalently bonded to a fluorine, oxygen, or nitrogen. FON, F-O-N. If it's anything else, hydrogen bonding is not going to happen. Hydrogen bonding can only occur if it's fluorine, oxygen, or nitrogen in the molecule, which sounds like it'd be pretty rare, but it happens way more often than you would think because of oxygen. Oxygen is in a lot of things. A lot of things have oxygen atoms as a part of their structure. So hydrogen bonding occurs way more often than you might think given that restriction, but it's out there pretty often. The more polar the molecule, the bigger the partial charges and the higher the boiling point. Okay? Again, this is Coulomb's law stuff, right? Partial charge goes up, bigger partial charges, stronger attraction. Now, since we're talking about intermolecular forces, the stronger those attractions are, the more difficult it is to boil a substance. They're held together more tightly. So to turn them into from a liquid, where those attractions are kind of taking place, right, to a gas, where they're completely separate, it takes some energy. The stronger they're held together, the more energy it takes to turn them into a gas. The polarizability of a molecule blanks when the number of electrons in the molecule with the number of electrons, it increases, right? The more electrons you have, the polarizability goes up. And this last part's new, I haven't talked about this. But if you have pi bonds, I won't use that term again. If you have double bonds or triple bonds, it actually helps it even more, okay? Things with double bonds and triple bonds are even more polarizable than things with single bonds. That doesn't really come up on the AP test, but it's true. Double bonds and triple bonds help the polarizability. They kind of make the molecule or the electron cloud bigger. So just something else to kind of consider in life. This is a very useful little chart. This shows a spectrum of the strength of intermolecular forces. The three that we have most focused on are London dispersion. They just didn't put the dispersion word. Fear not, it's the same thing. London forces are right here. They are very weak, okay, from weakest to strongest. So this is the weak side. As I go down the spectrum, I hit dipole-dipole forces. These happen with polar molecules. They are a little bit stronger than London dispersion. Then I hit hydrogen bonding. You'll notice that the dipole-dipole bracket has hydrogen bonding within that bracket. Hydrogen bonds are a type of dipole-dipole. Remember, let's go back. Dipole-dipole means that you have two polar molecules attracted to one another. Is that polar? The answer is yes, it is. Right? I could draw a dipole moment if I wanted to. That's the arrow showing which way it goes. Okay? Again, that points to the negative. The positive side means that the other side is positive. These are polar. This is a dipole-dipole attractive force. But it gets a special name because hydrogen bonding is slightly stronger than normal dipole-dipole. It gets its own special classification because they are uniquely stronger than any other type of dipole-dipole. But hydrogen bonds are a type of dipole-dipole. So you'll see this bracket encompasses the hydrogen bond. So weakest are London dispersion. Dipole-dipole, these happen between polar molecules. They're the next strongest. Hydrogen bonding are the strongest intermolecular force that we're talking about. The last one here is called ion-ion. That's an ionic bond. That's an ionic compound. If you have one positive, one negative ions, that's very, very strong, right? So these are quite literally like ionic compounds. Yep. Yep. I don't know why it's doing that. Okay. This is kind of fun. Or not. Okay, those are ionic bonds. That's an intramolecular force, right? Ionic bonds are stronger than intermolecular forces. That hopefully makes sense. That feels pretty logical. We could totally use Coulomb's law to describe this too. These have generally the smallest partial charges. Partial charges are bigger. Partial charges are really, really big. This is full charge, 1 minus 1 plus. Remember, partials are less than 1. So these partial charges are like closest to 0, getting bigger and bigger and bigger and bigger until you reach a full value of 1 positive, 1 negative. Bigger charge, bigger attraction. Questions? I have a problem through it today. I want to finish it. All right. Factors to consider. This is just notes. That's all this is at the tail end of this sheet. These are just kind of some pitfalls and some things to look out for as we answer some more questions about this stuff, okay? So, thing to consider number 1, what type of covalent bonds exist in the molecule? If you have HF, HO, or HN, you might have hydrogen bond. Again, you're looking out for FON. If there are any other polar bonds, you might have dipole-dipole. It might be a polar molecule. It just depends upon the shape. If there are only nonpolar bonds, then you will have just London dispersion forces and nothing else. Thing to consider number 2, how many electrons are in the substance? In general, greater molar mass, more electrons. More electrons, more polarizable, bigger attractive force. Okay? Use this comparison when you're comparing molecules with the exact same type of force. If I'm looking at something with London dispersion and London dispersion, the one that's going to have stronger forces is generally going to be the heavier one, the one that's bigger, the one with more electrons. Okay? Thing to consider number 3, how will the shape affect the surface area or the contact area? This is that last weird one between octane and the 2,2,3,3 tetramethylbutane, which is just kind of fun. Okay? Long, skinny molecules have more intermolecular force than molecules that are compact or kind of spherical or ball-shaped. This comparison is for isomers. Isomers, again, are molecules with the exact same formula, just arranged in a different manner. Let's try some. In this chart, I would like you to fill out the types of intermolecular forces for all of these. I've got 4 categories. One of them is ionic. We haven't really talked about that, but remember what ionic compounds are, right? Metal, nonmetal. That still works. That old definition from last year of what an ionic compound is still works. If it's not ionic, which there's a couple in there, then you might need to draw it out somewhere. Because understanding if it's polar or nonpolar is kind of a big deal. Polar molecules will give you dipole-dipole. Nonpolar molecules will be nothing but London dispersion. And that distinction sometimes requires us to make a shape so we know what the heck we're looking at. Okay? I've got a couple funky ones on here, like towards the bottom. But I'm going to let you try this a little bit. And I'll jump in and fix some things along the way. Go for it. See what you can do without me. See if you can identify any of these intermolecular forces without my help. I'll give you a couple minutes to get ahead of me. You're welcome to talk to each other. Obviously, the computer people, that's probably not an option. You can talk to your dog or your cat if you'd like. But for you in front of my face, you're more than welcome to chit-chat across the room. Obviously, you're socially distanced, but don't feel bad about yelling across the room. I don't care.
Everyone.
I'll help you with this one later. That one we'll just deal with later. Here's some formulas. That helps a little bit, I think, because again, we're gonna have to draw out a couple of these, right? If you need extra space, by the way, I know once again I haven't left a ton. There's a smidge on the bottom, but I think the back is open, isn't it? Noise. Okay, if you need the back to draw some of these out, totally use the back side of this sheet to help us. I heard it whispered in the front row. What do you want to do with the very last column? Everything. Everything has London dispersion. Nothing to think about here, right? Yes. Whammo. Everything has London dispersion. So we're good over there. Now it really comes down to some of the other ones. Let's, there is one ionic compound. Which of these is the ionic compound? You might need your periodic table. Remember what we're looking for, right? We're looking for metal, non-metal. Right. Francium fluoride, metal, non-metal. Now, again, you might not know that without a periodic table. But if you have a periodic table, francium's way down the bottom left, very, very metallic. Fluorine's way up in the top right, very much a non-metal. That's what we're looking for. This is your ionic one. Okay? Now let's systematically start plowing through the rest of these. NH3, that's ammonia. Okay? If I were to do a Lewis diagram of that, because the Lewis diagrams help a lot when we're trying to determine polar or nonpolar, NH3, how many valence electrons? Nitrogen has 5. Each hydrogen is 1, 8 total. Nitrogen goes in the middle. I need at least 3 bonds. That's an H, I swear. That took 6. I got 2 more to go. Hydrogen doesn't want any more. They're not going to go on the outside. They're going to go right there. What's the coordination number? 4. How do you count coordination number? You're right. That's right.
The atoms and then the lone pair.
Exactly. Yeah, exactly. It's how many atoms are you separating and how many lone pairs in total, right? So I've got 1, 2, 3 atoms, 1 lone pair for a total of 4. If it's a total of 4, that means we have a tetrahedral shape, right? But it's not 4 atoms. So I start with the tetrahedral shape for a coordination number of 4, but then I only worry about the atoms and not the lone pair. The lone pair replaces the top atom, and I'm left with that little trigonal pyramid, right? Okay, this is a trigonal pyramid. Polar or non-polar? It's polar. It is polar. If it's polar, what types of forces do we have going on here? What kind of intermolecular forces would we have? Do we have dipole-dipole if it's a polar molecule? Yes, we do. Hydrogen bonds, how do we analyze that? What are we looking for if we're trying to figure out if it has hydrogen bonding? It needs hydrogen, obviously, it's in the name. But then that hydrogen needs to be bonded to fluorine, oxygen, or nitrogen. Do we meet that criteria? We do. This has hydrogen bonding as well. Is it ionic? No, it's 2 nonmetals. Nitrogen and hydrogen are both nonmetals. So the other thing that I wanted you to do in this chart is put yes for all the forces that exist between the molecules. Circle the strongest. Which of these is the strongest type of intermolecular force within my ammonia. Hydrogen bond. That is stronger than dipole-dipole. That is stronger than London dispersion. Now, again, hydrogen bonding is a type of dipole, but it gets its own special name. All right, dibromofluoroborane, which sounds way more complicated than it actually is. This is like a boron with 2 bromines and 1 fluorine. Okay, there's lone pairs all around the outside, but there's no lone pairs on the central atom. This is a coordination number of 3 atoms, no lone pairs. What shape do you get for a coordination number of 3? Trigonal planar, meaning it's flat, right? You got a nice little flat triangle shape with 120-degree angles between your atoms. Polar or nonpolar? Polar. Why? You're right. Well, let me ask you this. Let me rephrase this. If all 3 of these were bromines, polar or nonpolar? Nonpolar. They would all cancel out, right? The electronegativity of the outer atoms would be pulling, in equal and kind of opposite directions, right? Because it's a perfect triangle, so the one would pull directly in between the other 2 and kind of cancel it out, and so on and so forth. But they're not all the same, right? We've got 1 fluorine and 2 bromines. Fluorine and bromine have different electronegativity. True story? So this guy is pulling with more strength on the electrons than these 2. And as a result, we do have a polar molecule. Do we have dipole-dipole? Yes, that's when you got polar molecules, you get dipole-dipole attractive forces. Hydrogen bonding? No, right? There's no hydrogen. It's already out because of that reason. Is it ionic? They're all nonmetals. No. This is the strongest type of intermolecular force in that one. Fluorine, F2. I don't think I need to draw this out, right? It's just a single bond between 2 fluorine atoms. Polar or nonpolar? Nonpolar. Do we have dipole-dipole? No. Is there any hydrogen? No. Is it ionic? No. All we have is London dispersion forces. I didn't write the word yes over there, but it's all we got. It's a nonpolar molecule. The only type of intermolecular force between fluorine molecules would be London dispersion, nothing else. Francine fluoride we already covered. It has London dispersion, but it's ionic. Ionic bonds are an intramolecular force. Those are substantially stronger than hydrogen bonds or dipole-dipole. It's an actual bond, right? When we say hydrogen bond, it's kind of like a fake bond. It's not real. It's an intermolecular force. But this is an ionic bond, and that is way stronger than any intermolecular. Sulfur dioxide. This one we're going to have to draw out. This one takes a little bit of brain power. Let's do a Lewis diagram. If you got some space on the front or on the back, let's do a Lewis diagram for SO2. How many total valence electrons do we have to work with? 18, that sounds about right. I haven't thought about it, but you're right. Sulfur is going to go in the middle. I need at least an oxygen on either side. That required 4. I've got, okay, that works, I suppose. I got 14 left to go. You always start on the outside. I can add 6, 12, leaves me with 2. Those have to go on the center. Now, formal charge is messed up. I am going to need to make some double bonds. It's actually a double bond on each side. Okay, and we can totally do that, and that's all well and good. Okay, that's the actual Lewis diagram of this molecule. But what's the coordination number? 3. I have 2 atoms, oxygen, oxygen, 1 lone pair. 1, 2, 3 getting separated around my sulfur. What's the shape of this molecule? It's not linear, right? I've drawn it linear, but remember, those diagrams aren't showing shape. Okay, they don't show shape. Coordination number is 3. These 3 things, the oxygens and the lone pair, would be separated in a trigonal planar arrangement. We ignore the lone pair and we just name it based off of what's there. This would be a bent molecule. Polar or nonpolar? This is polar. If it was linear, it'd be nonpolar, right? They would pole equal and opposite and it would cancel out. But this is not linear. It's bent. The oxygens are both pulling downward in this example. The left to right stuff might cancel out, but the up and down pull, both oxygens being pulled downward if we bend it that way, right? That's not going to cancel. This is polar. What do we have for forces? Do we have dipole-dipole? Yes, we do. Hydrogen bonding? Nope, there's no hydrogen. Ionic? Nope. We've got dipole-dipole as the strongest type. Sulfur hexafluoride. Which is SF6. That has a lot of valence electrons. It's 48, I think. Yeah, cool. Sulfur goes in the middle. We've done this one a bunch though, right? We've literally done this example like 4 times. So I'm going to go fast. No, I don't like that. Okay, F. There's a whole bunch of dots, so on and so forth. Coordination number. 6. What's the shape? Octahedral. Yes. Good. You still remember Unit 2 things. That makes me happy inside. Okay. Yes, this is octahedral. That's like 90-degree angles everywhere, right? 1 up, 1 down. 1 towards you, 1 away from you. 1 left, 1 right. 90s. Perfectly symmetrical. Polar or nonpolar? Nonpolar. Do we have dipole-dipole? Do we have hydrogen bonding? Is it ionic? No. All we have are London dispersion forces. Ethanol. All right, now you need some help, I think, right? Ethanol looks like this. And no, I would not expect you to know this. That is ethanol. Let's take a glance at that for just a second. Is it symmetrical? No, there's an oxygen on one side and there's not one over here, right? There's not symmetry. So is it polar? Yes, it is. Do we have dipole-dipole? Yes, we do. Could there be hydrogen bonding? Correct. Yes, there can. This is what we're looking for right there, right? In order for hydrogen bonding to be possible, we need a hydrogen bonded to a fluorine, an oxygen, or a nitrogen. These 5 hydrogens right here cannot do any hydrogen bonding. It's not going to work. They're hydrogen, that's all well and good, but they're not bonded to fluorine, oxygen, or nitrogen. There is one hydrogen that can. This guy right there, or girl, I'm sorry. This feller is bonded to oxygen. We can have hydrogen bonding in this molecule. Okay? So this is yes. Which is stronger? Hydrogen bonding is stronger. That's the strongest type we got. Carbon tetrachloride. We're almost done, I think. CCl4. We've done this one before too. Looks like this. There'd be lone pairs all around the outside of the chlorines. Coordination number is valence electrons is 32. No, you're good. Coordination number is 4. What's the shape? What's the bond angle? 90. The weird one. I say it's the weird one. Does that help?
109.
109.5. Okay. 109.5. Yes. It's tetrahedral. Polar or nonpolar? It's nonpolar. Okay. Now, this is a 2D drawing, right? It's not flat. It very much has depth. It's a tetrahedral shape. That's where you got 1 straight up and like 3 making a little tripod underneath the central atom. That's a tetrahedral shape. It's a symmetrical shape. That means it's a nonpolar molecule. Do we have dipole-dipole? No. Do we have hydrogen bonding? There's no hydrogen, so spoiler alert, that's not going to work. There we go. It has London dispersion and nothing else. That's the strongest type of intermolecular force that it has. Propane, 1, 2, 3 triol. Of course, you all know what that is. Right? No, looks like this. Yeah, how fancy do I want to get here? We'll go like this. That's an H, I think. We need an H over here too. That do anything for you? Now, it kind of sort of looks symmetrical a little bit on two-dimensional paper. It's really not, I promise. Okay. Each of the carbons, there's 3 carbons in a chain, making like a little chain, right? And each carbon has an OH group attached to it. Oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen, kind of like this one. Yeah, I didn't draw it like that. I just put them attached. This is not symmetrical. Therefore, it is polar. We have dipole-dipole. Is there chances for hydrogen bonding? Yes. We have a hydrogen bonded to an oxygen here. We have a hydrogen bonded to an oxygen here. We have a hydrogen bonded to an oxygen there. Again, these other ones, these 2, those 2, and that one, they would not do any hydrogen bonding with neighboring molecules. And the reason is because they're not attached or bonded to a fluorine, oxygen, or nitrogen. So only certain hydrogens can do hydrogen bonding. These 3 absolutely can. The other 5 cannot. Okay? It really matters what they're attached to. But we can do hydrogen bonding. This is not ionic. The strongest type we have is hydrogen bonds. Phosphorus trihydride. It's this, but with the phosphorus. Okay? There you go. Lazy teacher. It's the same shape, same structure, same number of valence electrons. It's a trigonal pyramid, polar or nonpolar. The shape makes it polar, right? Because it's not symmetrical. We got 1 atom in the center and then like 3 underneath it, kind of making a tripod. So this is a polar molecule. Sorry, I almost misspoke. It's polar. We have dipole-dipole. Do we have hydrogen bonding? Why not? Yeah, exactly. I got hydrogen. That's all well and good. But they're not attached to the right atom. It's not attached to fluorine, oxygen, or nitrogen. It cannot be hydrogen bonding. All we have, the strongest type, is dipole-dipole. So let me recap life, because I kind of came at you pretty fast today. We've got 3 major types or main types of intermolecular forces that we talk about. Hydrogen bonding, dipole-dipole, and London dispersion. Everything has London dispersion. Everything. Dipole-dipole attractive forces or intermolecular forces happen when you have a polar molecule. To figure out if you have a polar molecule sometimes requires a Lewis diagram and thinking about what shape it might be, right? I have a hunch you probably just can't look at SO2 and know that that's bent right off the bat. And if you can, stop studying chemistry in your free time. Because anyone who's not studying chemistry in their free time probably doesn't know that. Okay? So you might need to draw it out sometimes, and that's okay, because we learned how to do that. We know how to make a Lewis diagram. We hopefully can use that Lewis diagram and figure out what the shape's going to be. That's the hope. That's Unit 2 stuff. And then, once we know the shape, we can determine if it's polar or non-polar. If it's polar, you have dipole-dipole. The last type is hydrogen bonding. That occurs if it's a polar molecule and the hydrogen is attached to fluorine, oxygen, or nitrogen. Being able to identify what you got in terms of intermolecular forces is a big deal. And it helps explain a lot. It really does. This is a very useful thing that we're going to have to do on a semi-regular basis from here on out. Okay? We got 3 minutes. We'll sanitize. If you're still on the computer, thank you for hanging out. I appreciate your time. Have a lovely day.